So other than cash flow with multiple payment of the same value, we can also have cash flow which has a linear relationship. And for this kind of cash flow, we can also find a very simple way to obtain its future or present value. So here we have this linear gradient series where we have the value 0 at the end of the first period. Then from then on, every time we move one period, we add an additional of the value g. So the difference between each cash flow will be g. The difference stay the same, which gives us a linear gradient series. And with such kind of series, fortunately, although we are not going to derive it, but in fact you can actually derive it and get the formula that you see in the box. It's not that difficult. You can derive it, and again you can plug in I and n and compute the value. You probably need to use your engineering calculator to do that. But fortunately, at the same time, in the appendix of the book, you can still go to the page I with the interest rate I and find the column of given G, find P, and going down that column and find the corresponding n, then you get the coefficient directly. Okay, is that easy? You just see this series of cash flow. Again, it doesn't start from the present time. It starts from the end of the first period, which is still 0. Then for every period is increased, the value increased by g. That constitutes the linear gradient series. With this exact pattern, you can look it up from the appendix and get the index directly. So what does the series seem to have this pattern, but it's not exactly the same as this pattern. At least we have these two cases where you can see that the series to the left, you can see that it's linearly increasing. However, it doesn't have the exact pattern that we described previously, because here at the end of the period 1, it already has this value of 8. So we cannot use that formula or that table lookup method to get the value. However, if you think of it, such a series can be divided into two series, which added together will come to it. So you can see that for that series, if we subtract every cash flow by A1, okay, so we have this A1 series. The remaining will be exactly the same as we saw in the previous slide. That is starting from the end of the first period, which is 0, and then we have this increment of G, right? So if we divide it, the increasing gradient series into two series, we get one series of equal payment. The second one is just the geometric gradient, linear gradient series, and both of them can be obtained by computing their corresponding formula, or we can look up the coefficient directly from the tables in the appendix, corresponding table from the appendix. Okay, so that makes it a lot easier to get the value. For the decreasing gradient series that we saw on the lower part of this page, again we see this decreasing situation, which doesn't apply to the case we saw on the previous slide, but we can also divide it into two series. We can take this AI, which is the largest cash flow, and subtracting a series which is again identical to the series on the previous page. So with the AI, the big AI or A1, for the big A1 series, we can easily compute its present value or future value. Similarly, we have this linear gradient series. We can easily compute its future value or present value. So we can add them together to get the value of the decreasing gradient series. So sometimes we can decompose a series of cash flow, so that the remaining the decomposed part each will be very easy to be processed. Then we can process them separately and add them together or subtracting them, so that we can get the result more easily. So we can, and there's also another example where at the end of the first period it's not equal to 0. Okay, just as we saw previously. So we take 1000 equal as A1 and subtracting all others cash flows by 1000. So we can take 1000 and given A by P plus 250, which is the increment, and G. So we take given G by P2, and we easily look up on the table and get the coefficient and compute the present value. And then we can combine these two present value to get the overall present value. Okay, so if we think of it, we can still do this individual conversion, taking future value to present value, taking every single future value to the present value. So we compute 5 times, we add them together, we got 5204. If we use the previous method we just described, we can break the cash flow into 2 series. One series we can use given A find P, the other series you can use given G find P, and we can compute the 2 series and add them together, which also come to 5204. Okay, meaning that we can take a brute force simple approach to compute individually the conversion, or we can take advantage of the structure of the cash flow and utilize pre-calculated coefficient to help us to get the result quickly. And before that, we need to decompose the cash flow into well-structured cash flow, so that we can utilize the lookup tables. We can also look at the geometric gradient series. So in this series, the next cash flow will be of certain percentage more than the previous one. So you can tell that for the cash flow at the end of period 2 will be a cash flow at the end of period 1 multiplied by 1 plus G. So it will go up geometrically, as you can see. Well, in some sense, it's also fortunately that we can also utilize a lookup table methods or equation, and also lookup table methods to obtain the results. However, here it says that on one side, on the left side, when G is greater than 0, the cash flow go up. If G is negative, meaning that the value will go down, so they go in different direction. One goes up, one comes down, and doesn't matter which one, as long as G is the rate, increase rate. As long as the interest rate is not equal to G, okay, we can plug in the equation, the formula, to get the value, the coefficient value. Okay. If I equals to G, then, because if we still apply the first formula, we have I equal to G, so we will have a denominator become 0, and the value will become infinite. So however, if we sort of see if I equal to G, we know the effect, so we can even simplify that formula into the following one. So when I is not equal to G, there's a way to compute the present value. When I equal to G, there's still another way to compute the present value, so that we can easily obtain the present value, or then we can also get the future value. So here is an example, and following these numbers, you can plug them in. Here we know that G equals to 7%, and I will take 12%, so I is not equal to G, and we have A1 equal to 54,440, right? So we have that. We have N equal to 5, right? Because 5 periods, and then we can compute it's the result of the formula, and multiply by 54,440, we get 151,109. Okay, quite easy. We can just easily look them up and find the coefficient, or compute the formula to get the result. So with the earlier presentation on equal payment cases, then we can try to tackle many different kinds of problems. Let's just look at this example. We have a very unconventional equivalence calculation. think of you having paid a 4 annual deposit for 100 each, as you can see here. Then when you want to withdraw them, you will withdraw them in 4 different cases, 4 different withdrawn too, but at different time. Let's just say these 4 withdrawals are all of the same value, A. So the question will be, what should be the value of A? In order to compute, again, you probably have this idea already. That is, we need to compute an equivalence. These 4 deposits should be equivalent to these 4 A. These 4 deposits are of the same value, and these 4 A's are of the same value. However, they occur at different times. So there are many ways to do it. Okay, many ways to do it. And basically, we are looking at the equivalence of these 4 values and these 4 values. So this is what it means. These 4 100 should be equivalent to these 4A added together based on an interest rate of 10%. Okay. One way to do it, you can imagine, is we take these 4 100 and try to calculate its equivalent present value. Okay, try to calculate its equivalent present value. The way to do it, based on what we just learned, you know that we want to compute present value. Okay. This present value is equal to 100, which is of the equal deposit value of all the 4 years. What we want to find is, we are given A, which is this 100. We are trying to find P, and the interest rate is 10%, and the periods is 4. So we can look it up again in the back of the textbook and find the index and multiply 100 by the index. We get 316.99. The equivalence of these 4 A's require more processing. That is, if we apply the same, using the same symbols to look up from the table, what we can do is we can move these 4 cash flows to this point, assuming that here is 0 and they are 4 equal payments, and we can move all of them to this point. Okay, move them to the, so we can use, given A, find P 10% and 4 period, multiply by A, by this A. Okay, then we can get the value at this point, but the value at this time need to be converted to the present time. So this is the fact, to the present time is still a future. So what we can do is we take this value and multiply by given F, find P at 10% with 4 periods. However, we do not need to convert these equivalent, do not have to convert them to the present time for the derivation. In fact, we can convert them to any time. For example, if we choose the end of the fourth year, then we can convert this $100 equal payment to the end of the fourth year. Similarly, we can convert this 4 equal payment of A from year 5, 6, 7, 8 to year 4. If we convert them to the same point, the same time point, they should have the same amount because they are of the same value. They are economically equivalent. So we can convert it to any point. So this is also a very, very good point because we just need to take the first series of the cash flow as 100. We just need to convert them into the future value. And for the second series of equal value A, we only need to convert them to the present value. So what we can do, as you can see, for the first sequence, we just need to take given A, find F, 10% and 4, using 100 multiply, we get 464.1, and it has to be equal to, if we take these 4 A's and convert them to the end of period 4. So these 4 of A need to multiply given A, find P, the end of year 4 to this series of the cash flow is equivalent to the present time. So we are given A, find P, 10% and 4 period. We can again look up and get the index and multiply by A. It becomes 3.1699A, and 3.1699A need to be equal to 464.1, and we can solve for A, and A is again 146.41. Okay, so this method putting to a middle point, or the previous methods pushing everything to the present time, or we can push it all the way to the end of the 8th period, or 7 or 6 and 5, or even 3, 2, 1. Doesn't matter where we push them to the same point, because these two series of cash flow need to present the same words. So doesn't matter where you convert them to, they should give the same value there. And then by solving the equation, you can get the same A, which is 146.41. If you go back to the previous slide, you can see that it's 146.41. Doesn't matter where you take them. Okay, so very importantly, here I want to emphasize, if they are equivalent, you can take them to any time point. That if two series of cash flow are of the equivalent values, equivalent words, doesn't matter where you convert them to, they should have the same value because they are of economic equivalence. Okay, so at any point in time you look at them, they should be the same.